Well, drive-by geology is the best kind of geology.
Oh, exactly, yeah.
You're listening to The Cosmic Cast.
Hello, and welcome back to The Cosmic Cast. I'm John Perne Fisher, and this week, as my lovely co-hosts is Elliot Carter and Marissa Lowe.
Hi.
And this week we're joined by Matt Varnam. Hello. How's it going?
Yeah, good. How are you?
Pretty good, thanks. So you are a volcanologist.
Yes, that's right.
And
So-
you're in your final year now, aren't you?
Scary.
Also in your final year.
Yeah, final year of PhD. So getting to the crunch time, I guess.
So tell us about your project then. So you're working also on Stromboli?
Yes, so we're both me and Ben, who I believe has been on in a previous week, been working with the Italian Geological Survey. So they're called INGV, and we're working with a specific branch that works out of Sicily. And so they're kind of in charge of a lot of the volcanoes around Sicily. So there's Etna, that a lot of people have heard of, but also some of the Italian islands. So you've got kind of Stromboli and Volcano, and then some other ones that aren't really very active. Maybe like Lipari as well. I'm not sure if it's classed as an active volcano, but if it was, they would be covering it.
Because I've got a very romantic view about fieldwork in Italy, which is just sort of sitting around with straw hats, drinking wine, and
Yeah, so I think for some people it's probably quite intense. But so I work in remote sensing, so we like to stay quite a distance away from the volcano, and then set up some cameras. So I work with something called the SO2 camera for detecting gas. And there we usually set up around 3 or 4 kilometers away from the volcano. And the thing that makes that especially nice on Stromboli is 3 or 4 kilometers puts you right about the base of the volcano by the beach.
very nice, very nice.
Oh, very convenient.
Yeah, very convenient. And also there's a really nice restaurant there as well. So, you know, you sometimes have to go in.
That's going to sound very scientific in any papers of yours. You'll be like, we had to be 3 to 4 kilometers away from the volcano to be next to the restaurant. Yeah.
And actually, we used some of their umbrellas as sunshades in our most recent trip.
Got to keep out the sun.
Yeah, well, we'd found in some of our previous trips that when you don't have the umbrellas there, you don't block out, or you get a sort of lens flare in the camera due to the sun being in the way. So, you know, we have to be there.
You have to have a cocktail in your hand.
I have to have that delicious plate of pasta.
Yeah.
But no, they're just the perks of it. I mean, I make it sound super easy, I guess. But there is a lot of, you kind of wake up quite early so that you can get to the volcano for your kind of the optimum viewing hours.
Right.
I remember one of the trips we did into Guatemala, going to Santiaguito volcano, or it's on the flanks of Santa Maria, which actually had one of the biggest eruptions in the 20th century. Like absolutely huge, like bigger than Mount St. Helens. And this volcano tends to has a problem of cloud comes in quite consistently about 12 o'clock. And so you have to be up at like the crack of dawn so that you can then start walking kind of pretty much in the dark all the way down to the kind of viewing spot that we went to. So that was about a 2 or 3 hours walk, and then you set everything up, and then you only have a very brief time period of the sun being up so that the cameras can get enough light in, and they're not just being a huge bank of cloud coming in and swallowing you up.
So Matt, why do you look at SO2?
So the main reason we look at SO2 as opposed to any of the other gases,
That's
so
sulfur dioxide.
yes, sulfur dioxide.
Okay.
So the 3 main gases coming out of sort of a hot volcanic plume are water, H2O, which is then second is carbon dioxide, and those 2 are the kind of very biggest. Those are the 2 biggest gases, and then next comes in sulfur dioxide. So you might think, well, why do we choose sulfur dioxide as opposed to water or carbon dioxide? Well, the problem with water and carbon dioxide, I mean, with water, there's a lot of it in the atmosphere. That's how we get rain, and there's always some water vapor around. And then carbon dioxide, we're increasingly pumping more carbon dioxide into the atmosphere every year, and so you don't get a sort of stable background to view these other gases. And in fact, the amount of gas that's in the plume is completely dwarfed by the amount that's in the atmosphere. So you have very little hope of imaging it. There's, I think, one person who's actually managed to convincingly kind of image, I think it was water vapor.
Wow.
But they had to go to sort of the very highest deserts in Chile, where you've got rid of most of the atmosphere by that point. So, I mean, it's much, much easier to see sulfur dioxide, which just isn't in the atmosphere around us. It has we emit it from things, we used to emit a lot of it from power plants, and then that would
like burning coal and stuff, isn't it?
Yeah, burning coal. So there was a huge problem, before I was born, but with acid rain across Europe that they then had to deal with scrubbing out sulfur dioxide from the atmosphere. But the reason why you get that is because the sulfur dioxide goes into the atmosphere, and then it will form sulfuric acid while it's in the atmosphere, and then come down out of the atmosphere as the acid, which was so harmful. But that is the process that removes it from the atmosphere, and so that's why it's not just around us all the time. Yeah. Thankfully, that sulfuric acid atmosphere would be quite horrible, I think.
So you're using it as a proxy for other gases, then?
Yes, yeah. So we use it to work out kind of how much gas is coming out of the volcano in total. It's standard practice you take the sulfur dioxide flux, so the amount of gas that's coming out of just one gas, and then you multiply that by results from other instruments that measure how much of each, like relative how much of each gas there are. So they can't measure the total mass of gas coming out, but they can pick up the carbon dioxide to sulfur dioxide ratio that's in the plume. And so by kind of multiplying that together, you can get some idea of the fluxes of every gas coming out of the volcano. So you can get, beyond the water and carbon dioxide I was talking about, there's also, you can get some of the hydrogen fluorides, hydrogen bromides, hydrogen chlorides, whole list of gases that can be detected this way, and all of them can tell you something useful.
Yeah.
So that was what I was going to ask, is what then do you do with that information? Why are people so interested in gases coming out of volcanoes? Just in very simple terms.
Yeah, good question. So when you have I suppose the simplest way of talking about it would just be kind of just amount of gas, and that can be used for some predictive capability. So if you see a big spike in the amount of gas emitted, then that could tell you that there's more magma underneath the surface that's able to release these gases, or maybe it's telling you there's a lot of ambiguity in some of these signals, but they do tell you something. So so it could be more magma underneath the surface. There could be the magma is overturning, so circulating more quickly in the chamber, which will help it release gases much more easily. And you could also have a rising magma body as well, and that would help relieve the pressure. So like when you open the lid on a bottle of Coke and all the gas starts coming out, same with magma. If you raise it up, then lots of gas will start coming out. So then when you want to start to tell the differences between all those different scenarios, that's when you start looking at all the ratios of the different gas fluxes. In simple terms, there's a sort of order, things like being dissolved in the magma at different amounts, and so deep down carbon dioxide is released quite early, and then as it rises, then you get sulfur dioxide coming out more, and so kind of by comparing how these different fluxes of gases change over time, you can build up a picture of what's happening deep down under the surface of the Earth. And it's probably one of the the best windows that you have of actually getting kind of inside that magma chamber, if you like, and seeing what's going on there.
And you can apply this to all sorts of different volcanoes. It's not just specific to a certain type of volcanism, or
no. So different types of volcanism will produce different sort of effects as well. So one thing you tend to find is a lot of the basaltic systems. So they're very silica poor, runny. Think your Hawaii's. There you tend to get more open. It's not a universal rule, but they tend to be slightly more open system. You get more basaltic open system volcanoes, which means that they're constantly releasing gas. And so kind of you can look at those kind of changes of gases. But then when you have your thick, sticky magmas, kind of St. Helens, Mount St. Helens, then there you're more likely to be building up pressure. And in fact, for kind of your Mount St. Helens, is detecting any sort of gases or like sulfur dioxide means that there is magma very close to the surface. So actually they can tell you very different things. Hawaii, if you see gas coming out, that's normal. Mount St. Helens, if you see gas coming out, it's like, oh god.
Run for the hills. Or away from the hills.
Away from the hills.
It's interesting you were saying how the different gases are gonna like come out of the magma at different heights, because that's sort of what I'm looking at for my project for magma sent on the moon. So looking at how the solubilities of the different gases, so the ones I'm looking at are water and carbon monoxide. Thinking about how the solubilities of those change depending on the composition of your magma, and also how the pressure differs. So what sort of depths you're at.
Sorry, is carbon monoxide just because there's not as much? Well, there's no oxygen on the moon, or
so the carbon monoxide on the moon is thought to come from the oxidation of graphite.
Okay.
I guess that's the thing with the moon, is that there are so many more unknowns relative to a terrestrial system that you can just study.
Yeah, but it's interesting how you're looking at what comes out of volcanoes and thinking about, what depths do different gases exsolve? And that's exactly what I'm thinking about too. Because obviously in my models, it's giving us a handle on what were the eruption conditions when this magma finally reached the surface, what rates was it coming out of the vent, and gases has a huge effect on that.
Yeah, it must be a lot harder on the moon because it's not active anymore, so you don't get to just sit and watch the volcanoes erupt.
Exactly. We've not witnessed
what's coming out.
We've not witnessed the live eruption. So
it's a lot of unknowns. I guess a lot of the gas species are not too known as well, or what might be present as well, because you can't just measure that, unfortunately.
It's quite dubious data, mainly looking at coatings of different pyroclasts from the moon, but again they're in such small amounts that it's very hard to measure them.
It must be very tricky.
But they certainly would have been quite gas rich though. So I mean, some lunar basalts are very vesicular in nature, so there was obviously quite a lot of gas being degassed. Gas being degassed. Okay. So when you're imaging these volcanoes, then are you able to sort of build up a three-dimensional picture, or are you just looking more at sort of 2D transects?
So I tend to work with 2D transects. So we only have one camera deployed on the side of the volcano, and to get some idea of the three-dimensionality of it, you'd probably need more than one in one location. I don't know what the kind of minimum amount would be. I think some people have tried it actually, and trying to come up with some sort of it'd be called tomography of the plume. So kind of like how a medical scanner works to build up a picture of your body by kind of scanning it and from all directions. You could probably try and do something like that with the plume as well, maybe to try and help figure out some of the dynamics. But usually with the cameras, we're just focused on how much gas is coming out of that volcano, and so we only need to do that from one spot.
So how do sulfur dioxide cameras work? Obviously, to me, a camera, you take a picture and it's just looking at everything in visible light, but what does sulfur dioxide camera mean?
So I mean, the basic part of it, just the sulfur dioxide is it images sulfur dioxide, but I guess the question is, how does it do that? So they are ultraviolet cameras, so they work in kind of wavelengths that our eyes can't see, sort of much or slightly higher energy, the stuff that burns your skin. We're kind of using that light from the sun. And then we have to use 2 cameras side by side to make one SO2 camera, which sort of sounds a bit strange because there's 2 cameras in the camera. But so on one of them, you look at a wavelength of the UV light that is sensitive to sulfur dioxide. So at that wavelength, a big blob of sulfur dioxide in the sky will absorb some of the light from the sun, and so it appears as a black blob.
Oh, okay.
The problem is, like when you're looking around in sort of day-to-day life, you can see that lots of things absorb light, and all vary at different wavelengths, and that's why you have all the different colors. So actually what we do is we then select another wavelength, and this is for the second camera, that's quite close in wavelength to the previous one that was sensitive to this sulfur dioxide emission, but this one's not sensitive to the sulfur dioxide emission. It's like as close as you can possibly be to the sensitive bit without actually being sensitive to the sulfur dioxide. And then you can use that to cancel out everything else that's in the sky. So clouds and water vapor should get cancelled out by that. So both of the cameras see the water vapor the same, but they detect the sulfur dioxide differently, and so that's what you're measuring. Yeah.
Okay, so the final images that you'll end up with will be with your nice volcanic vent there, and then the black blobs for where the sulfur dioxide is.
So ideally, the volcano should be kind of equally reflective in both. So in the ideal circumstance, the only thing you would see in the final image is the blob of gas.
Okay.
Doesn't always work like that. There can be lots of differences and like small changes that mean that things like the hillside can still appear in your image. But thankfully, you can just you know that there's no, or you try and set up in a location where that doesn't matter. Yeah. So you can just see the sulfur dioxide and nothing else.
That's really cool. So what's the smallest amount of sulfur dioxide you can measure in the air then?
So we like to use a unit called ppmm, which is a sort of unit of concentration but along a path. So
parts per million per meter.
Yeah, parts per million meter. So
Right.
it's rather than per meter, it's meter.
Right.
That's hurting my head.
Yeah. So imagine, about the minimum you can detect is around sort of 50 parts per million meter.
Right.
So that would be 50 parts per million of gas for 1 meter.
Okay, I see.
Oh, okay.
Yeah.
But you have no information about sort of how deep it is. So it
sure.
could be 50 parts per million across a meter, 25 across 2 meters.
Yeah.
Okay.
Or, smaller, bigger.
Yeah.
So you don't get like the distribution, do you mean?
Yeah, so you don't. That's how. You only get it along a single line. So the distribution bit, if you wanted to come up with a sort of specific concentration map, you would then need a second, like 2 or 3 cameras and going back to the tomography that we were talking about earlier, where sort of imaging it from multiple angles and trying to reconstruct what those concentrations are. Yeah.
And how do you then? Because you have a picture, how do you then turn that into, say, like a flux or coming out? Because you've just got a picture of a cloud. How do you turn that into data?
All we do have is a picture of a cloud there, so you have sort of an amount of SO2 in a cloud. To get that into a flux, you need to multiply it by a wind speed. So how fast is the wind going? And so you then have you would draw a cross section through your plume, work out how much is in your cross section, and then get your perpendicular wind speed, and then that produces a flux. Unfortunately, that wind speed element is actually very tricky. Originally, people did it off weather forecasts, and everyone knows how accurate weather forecasts are. But recently, there's been a lot of work on using the camera images themselves. So with one image, you can't get any motion. But with 2 images or 3 images or 4 images, you can track the same point in the sort of cloud shapes across multiple images. So it's kind of like a way a speed camera might work, in that, it will try and take lots of, maybe take a video of a car that's going through it.
Yeah.
And then go, this one's... Actually, I don't think that's how speed cameras work, but never mind. Look at this car moving, 1 picture, 2nd picture, 3rd picture. It's moved this far across these pictures. I know how fast I'm taking my pictures. So that's how fast it's going. It's traveled 3 meters across my 3 pictures. It's only traveling 1 meter per second.
Yeah. That's cool, yeah.
And I've definitely seen some nice videos in your talks.
Oh, thank you.
They're always
you can draw some nice little arrows on your images that show kind of where all the gas is moving instantaneously. So it's not just a single wind direction. You actually have the wind for each pixel of your image.
Yeah, they're the ones that you have where it's just lots of arrows like flying around your image.
They do look a bit crazy.
So we talked mostly about Stromboli then. So I guess you've also visited a whole range of different volcanoes.
Yeah, so we've done the sulfur dioxide camera measurements on Etna, on Stromboli, on Messiah volcano, which is basaltic.
Right, is that in Italy as well, is it? Or?
No, that's in Nicaragua.
Okay.
Oh yeah, we heard about it.
Yeah.
Then the Santa Maria or Santiaguito lava dome in Guatemala. And then we also took them to Montserrat. Montserrat was a little challenging because it's a very tropical climate, and so there was just clouds all the time.
Yeah.
Which is, I said, like the camera should eliminate cloud, but when the cloud is just completely blocking out the light, like all the UV light, then it doesn't work, unfortunately, very well there.
So you're saying that INGV, the Italian Geological Society, monitor a lot of the volcanoes.
Yes.
How does volcano monitoring vary across all these different volcanoes and countries that you've been to?
Yeah, that's a great question. So there's an absolutely huge range of personnel capabilities, resources that all these observatories have open to them. So, for example, INGV is I think is quite well staffed. They've got a good infrastructure network on their volcanoes like Etna. So they're permanently monitoring small earthquakes around the volcano that might lead you to think that magma's rising or it's built up enough pressure to start breaking the rock a little bit. And you hear in the news of kind of magnitude 7 earthquakes. We're detecting things like magnitude 1 earthquakes, and each point on those magnitude scales is like a factor of 10 increase in the amplitude and a factor of 32 increase in the amount of energy.
Wow.
And so the scale of these earthquakes is tiny. In fact, there was a bit of an outreach activity we did, kind of communicating with the public, where we took a seismometer and just put it in front of people and said, make the biggest earthquake you can near this sensor. And people were getting magnitude -1. So you're looking at 30 times 30 more energy than that, which is not actually that much. Stamping on the ground.
Well, you hope it wouldn't be too much energy released from that.
Yeah. Depends how energetic the kids are that day. But yeah, so they're kind of constantly detecting these mini earthquakes. They're constantly detecting how much the flanks of the volcano move over time, using kind of GPS locations and satellite monitoring.
So basically, all the kinds of techniques.
So yeah, they're very much up there. Places like or all of the America, like USGS, Hawaii, they have some really great stuff out there. Kind of state-of-the-art equipment. And actually, I think sort of the Nicaraguan observatory that we worked with, they're not quite as well equipped. So instead of having sort of 30 or 40 seismometers on a volcano, they're looking at sort of 4 or 5, and instead of a network of 9 or 10 gas monitoring stations all around the volcano, you're looking at sort of 1 or 2. But they've definitely got some state-of-the-art kit from universities going out there and kind of providing stuff to help collect data, but they just don't have the sort of same resource level as.
So it just comes down to funding ultimately.
A lot of it does, yeah. I mean, other places have very specific problems. So I met a guy from the Democratic Republic of Congo monitoring agency, and there they have two big volcanoes that they're looking at, Nyamulagira and Nyiragongo. I'm sure I butchered those pronunciations. I'm sorry to anyone out there who knows the correct pronunciations. But there, so Nyiragongo is very close to the city of Goma, which has about 3 million people, and it can produce these really fast lava flows that come down the flanks. And so Nyiragongo is quite easy for them to get to, but if they ever want to go to Nyamulagira, which is like right next door, they have to go through kind of armed insurgents who are in control of that entire area. So they cannot actually go and sort of service some of their seismometers. If they break, you're looking at a really heavily armed kind of convoy trying to hack through jungle to get to some of these places. And there's a BBC documentary, Expedition Volcano, where they actually go to this second volcano. They had to take a helicopter all the way there, and then have a guy kind of watching out for anyone kind of coming up on around the crater, because they're just at the very top of the volcano, so they're kind of watching the crater permanently, on a lookout to make sure no kind of armed people are coming up. And then they also have a time limit. They're like, people will have seen our helicopter. We have to get out in 3 hours, which is how long it will take someone from the base of the volcano to get up to the top to get us.
That sounds quite stressful.
Yeah. And this is one of the most active volcanic systems in the world.
Yeah. Is this one of those ones with like really huge volatile output?
So Nyiragongo has the largest lava lake in the world. I think it's maybe 800 meters across, so just 800 meters of just solid, well, not solid, liquid liquid lava churning constantly.
So why is there volcanism in Central Africa? I'm just trying to think why that would be.
I think it's part of the Central African Rift system.
Oh, okay, right.
So the sort of east bit of Africa, it's not kind of cut it in half and take the eastern half. It's a small section of it is breaking away slowly. So you've got a whole sort of rift system there running from kind of Ethiopia all the way kind of through Central Africa.
Is it part of like Kilimanjaro and all that sort of chain of volcanoes?
I think so. Don't quote me on it. So I think that's all coming from the sort of same spot, or the same kind of rift system. But it's a very kind of early stage rift, and I think there's some hotspots feeding some of those volcanoes as well.
I think there's a plume under East Africa.
There's a plume in under Ultraviolet volcano, which is sort of, if you draw where the Red Sea comes down and then it takes an abrupt sort of 60 or 120 degree turn. There's a hotspot kind of at that.
The Afar plume.
The Afar plume. Okay, this is really testing my geology. Okay.
Geology and geography.
I'd love to go to some of these remote locations. Actually, it must be super interesting to like really get into like proper like middle of the nowhere big volcanoes. That sounds awesome.
Yeah, I mean, I've never been, but definitely would love to go. Although it does sound quite scary as to all the things that are going on there.
So is Nicaragua quite accessible then in some of the volcanism there?
So when we went, which was at the very beginning of 2018, very accessible. We just flew into the capital city, and then it's maybe an hour or less drive to the volcano. And actually this volcano Messiah is literally like a drive-in volcano, so you could drive up to the edge of the volcanic crater and look down into the crater.
That sounds fantastic. Well, drive-by geology is the best kind of geology.
Oh, exactly. Yeah, it's fantastic. I mean, it's crazy that this thing exists, right? You could just look down into an active volcano.
Yeah, just make sure you leave the handbrake on.
Recently, it's become a little bit less, probably a lot less accessible, because unfortunately there's a town near Messiah Volcano, also called Messiah, and that was actually in the centre of some of the political unrest there recently. So there's actually been quite a few projects that have had to be ended just because of this unrest. There was a whole project that was looking at the gas emissions from the volcano and how it affects the downwind communities, because there are actually people who are living on within some of these kind of areas that get constantly bombarded with these gases, and look at some of the sort of adaptation they've had to do. So they've had to switch all their crops because the soil's become a lot more acidic, things like that. And how is this affecting their breathing, and do they see any sort of long-term problems? But unfortunately, I think they've had to either scale it back or stop completely that program. It's a shame, but I mean, it was a very accessible volcano for us. And hopefully will be again soon. Letting people just drive in and see a nice active volcano.
Drive through volcano.
Yeah.
So what's been your favourite field location you've been to?
My favourite field location? Ooh. I mean, Strombley has got to be up there. But actually, I did, when I was doing my master's project, I worked out in Hawaii for 3 months.
Oh, cool.
Wow.
So working with the USGS on Kilauea in the Hawaiian Volcano Observatory.
Nice.
And we I was living in a house that they provide some accommodation for their volunteer scheme, and that's on the edge of the Kilauea caldera.
Wow.
And then you just walk to work around the volcano every morning.
Yeah, that's awesome.
That's really
Sit down, and then I was doing some seismic work, looking at a previous eruption and trying to see, what could we detect before the eruption? Could we see the magma moving through the system in 2011 before what was actually a relatively small eruption for Kilauea? As it turned out, I mean, it's now. There was a big one in 2018 where a whole lot of magma flooded out, and I mean, it basically drained the entire system. This was relatively small in comparison, but we're just trying to see what kind of early warning systems there were, and whether we could detect where the magma was going to come to the surface in advance, because you sometimes see this build up in seismicity that and earthquakes that's not really related to where it's actually going to break. It then kind of jumps just before it then erupts. So we're trying to track that and see if we could see anything.
So did you see any flows or activity while you were at Kilauea?
I saw what was technically a flow, I guess. So it wasn't moving very fast. So at that point, there'd been a breakout, I think, about a year before. So what I mean by that is basically the system that had made a new kind of break in the side of where it was pouring out lava. So actually, I should probably go into a little bit about how that kind of system works. So you have the crater at the top where you see a lava lake, but then actually maybe 10, 20, I think it's 10 or 20 kilometers or some crazy distance away from that was actually where all the lava was coming out. It wasn't coming out at the summit. It was coming out down what's called a rift zone. So where just, Hawaii's this big pyramid of rock, if you like, and the side of the stuff, it's just, it can't hold itself together. So the entire kind of flank of it is falling away. And that provides a nice easy route for the kind of magma to work its way through, and then it comes out halfway up or it came out sort of halfway down the volcano. And then actually what happened in 2018 was it drained all the way down to the roughly down at the bottom area. So draining all that kind of extra distance or extra height of magma.
Is it quite hard to predict where these breakouts will occur then? Because
they have no idea really. In advance you can't say it's going to come out here. But it was actually quite consistent, being sort of centered around an area called Pu'u'o'o, which is a great word. So there's this Pu'u'o'o cone, and all of the it was kind of breaking its way out there, and then it would flow either down towards the sea, which unfortunately I didn't get to see because that's apparently really cool.
Yeah, I'll bet.
Or sort of backwards and then towards some of the towns and villages that are in the way. So I think it was about a year before I went, so that would have been about 2014, 2015. A lava flow had just gone down and reached the outskirts of a town and then frozen solid just as it reached the town.
Yeah.
So there's the recycling station there. There is a burnt chain link fence. Lava has kind of pushed its way through that, started flowing down the kind of little ramp into the transfer station, and then frozen solid.
Well, that's pretty lucky.
Yeah.
Wow.
Yeah, and then behind that, the whole thing sort of then solidified.
Yeah.
And it was still sort of kind of coming out a bit further back.
Yeah. Do they cool quite rapidly then, these kind of things?
I mean, they're quite hot, but they move. I think they do take quite a while to cool fully. So the outside forms a crust very fast.
Yeah.
But then the inside stays warm because it's kind of insulated by the outside, so you form like little bubbly bits, and those little air pockets help insulate the whole thing.
Yeah, I need to look up how long it takes for lava flows to cool, because I was at Etna last Easter and we were studying like the 2011 eruption of Etna, and our lecturer, we got to the site and he was like, "Ooh, feel the ground, it's still warm, isn't it?" And we all just gave him a look like, it's been 7 years. It doesn't take 7 years for the lava to cool, but he was really trying to pull our leg about it.
Depends how thick it is, right?
It was...
With the leg or... So presumably someone comes around with a big stick and just sort of pokes it to see if it's solid all the way through. I mean,
I guess. I don't know.
Yeah, that's what you do.
I mean, they did
have to
spend a while like working out when they could bring the bulldozers, because it cuts off, these lava flows can cut off communities, and so you need to rebuild a road. And so it's just like, okay, we need to bulldoze this big block of basalt, or at least flatten it out a bit. Like, when can we first do that, and when can it support a bulldozer?
Yeah, I mean, I guess with these encroaching lava flows, it's like very slow motion disaster, isn't it? Really,
in most places, yeah.
Because can you outwalk a volcanic lava flow?
In most cases.
Depends
so actually, one of the
is.
it depends what it's made of, as I think Marissa was about to say. Sorry, but there are volcanoes that are exceptions to that.
Sure.
So I was talking about Nyiragongo earlier. That has lava flows that go in the tens of kilometers per hour.
Yeah, maybe getting your bike for that one then.
Yeah, yeah.
Yeah, and it's not just the lava.
Or don't go for your Prometheus walking, going away from disasters. Go sideways.
But yeah, it's not just the lava. You know, you get mud flows like lahars, which move very quickly as well. So
yeah, they can all be in lots of different hazards that you can get. I mean, these places that produce these big lava flows that tend not to have too many other large hazards associated with them that can spread out that far. But you know, there's always exceptions, and that's actually one of the kind of deadliest parts of volcanology, I guess. You know, you come up with all these rules as to how everything's supposed to behave, and then something does something that you don't expect, and that's when all the problems happen. You know, there's many examples of it. You know, Mount St. Helens volcanoes always erupt upwards, and then this one didn't. It erupt sideways, and that's where all the problems came from. People always kind of associate what a volcano always does with what it will do every time in the future, and you sometimes end up missing some of these strange hazards where one event causes something else, or things do unexpected things. Volcanoes do unexpected things, and that's really when people get kind of caught out, I think.
So Matt, if you weren't trotting the globe looking at volcanoes, what other area of science or outside of science do you think you'd want to go into?
What area of science or not science? Ooh, it's interesting because like when I first wanted to go to uni, I was like, oh, I'm going to do physics, and then that didn't happen at all.
Yeah.
I did a first year of natural sciences where I did some physics, and I just didn't enjoy it at university level. So you know, previously I would have been talking about, when I was kind of before undergrad, I would have been saying, like, oh, you know, all the physics. Would have liked to go into sort of some of the particle physics and maybe astrophysics as well. But now it's just, I don't know, maybe something a bit very different, like marine biology. That sounds quite fun.
Yeah.
Dealing with fish.
Swimming with dolphins.
Yeah, swimming with dolphins.
Yeah.
See a trend in the way, I think. But
what ways can I get outside and do science?
I do quite enjoy that, actually, because I think there's something special about being able to get a proper grasp on sort of the scientific questions you're asking.
Mm-hmm.
You can see it in front of you. Like, Marissa, you're looking at the moon. The moon's up there. Like, why?
Yeah.
I mean, it sounds like quite a silly question, I guess, but then it turns out there's these whole stories of planetary collisions in the early solar
how did
system.
the moon get there?
Yeah, exactly.
Why does that volcano look like that?
Yeah.
Why is it erupting?
Why is it in my back garden?
Exactly. These are problems you can see with your eyes and try and work. You want to work out why it works like that.
Absolutely.
And I think
it's a quest for knowledge.
Yeah, that was something that I maybe found missing when I was doing physics. Not to slight on physicists. They, in a way, they're kind of much more imaginative than me. They can imagine all these problems at the kind of either particle level or cosmological level.
Yeah.
And then I'm just kind of, I just want to know why that volcano is doing what it's doing. How can we work out when it's going to erupt?
Yeah.
Perfectly reasonable, I think.
Yeah.
Well, thank you very much, Matt. I hope you've enjoyed being on the podcast.
No, it's been a pleasure. Thank you.
So thank you very much, everyone.
See you next week.